All right, we're going to talk now about exponential functions, and we're just going to introduce first off the basic form and do a few simple graphs just to get an idea of what they look like. So first off, the general form that we're going to use is y equals a times b to the x. So the reason why it's an exponential function is because the x is up here in the exponent. And a couple things we have to watch out for. A cannot equal 0, because if a equals 0, then the entire thing would equal 0. B must be greater than 0. And finally, b cannot equal 1. Alright, so with that out of the way, let's talk about what do a and b stand for. Well, first off, let's tackle b. If b is greater than 1, and we'll see this work out in our graphs, then we're going to have something called exponential growth. Things are going to grow exponentially. And if we have b less than 1 greater than 0, remember because it has to be greater than 0, we have something called exponential decay. Exponential growth, exponential decay. So basically you just have to watch for this guy. B is going to be either your growth or decay factor. Okay? Growth if it's bigger than 1, decay if it's between 0 and 1. And finally, a. What is a? A is your initial value. By initial, I mean at x equals 0. Right? So a is kind of your starting point. So if you're timing at x equals 0 at the beginning of your time, your value of y is going to be a. And let's talk about why that is. Why is a the initial value? All right. Well, if we think about it, if we're doing something with time, for example, and if x equals 0, right, that's your beginning of your time, so let's just plug in 0 to this guy. So you'd have y equals a times b to the 0. A times b to the 0. Remember, order of operations, we do the exponent before we do multiplication. So b to the 0, well, anything to the 0th power is just 1. So y equals a times 1. So y equals a. So we can see at time equals 0, your initial value, or whatever it is, you're just going to have your output be this a here. Alright, so let's do a couple of graphs then. Start off here, y equals 6 to the x. Y equals 6 to the x. And the easiest way that we're going to do these is just with a t-chart. So let's just make a t-chart here, if we can see these guys. So we'll just make a t-chart with some values like -2, -1, 0, 1, and 2 for x. So -2, -1, 0, 1, and 2. And I'm going to hold off labeling my y's because I'm not sure how high these guys can go. They can jump up high really quick. So first off, let's take a look at this. What is our a, our b, everything like that? Our a is just a 1. Our a is a 1, so we know our initial value is going to be 1. Our b is 6, so we know since it's greater than 1, this is going to be exponential growth. Exponential growth. All right, so let's take a look. Let's just plug in. So if we plug in 6 to the -2, right? 6 to the -2. Well, what is 6 to the -2? Anytime you have a negative exponent, it can go to the denominator. We have 1 over 6 squared, or 1 over 36. 1 over 36, so a very tiny number. -1. 6 to the -1. Well, that would be, again, negative exponent. You can send him to the denominator. That's 1 over 6 to the first. So that's 1/6. All right, next up, 0. 6 to the 0th power. Well, anything to the 0th power is just going to be 1. 6 to the first is just 6. 6 squared is 36. So let's go ahead and graph these guys. Now that I know that my highest point is 36, let me just think about these. Maybe I'm going to count these by not 1 or 2. Let's do 4s. So 4, 8, 12, 16, 20, 28, let's see, 32, 36. Okay, is that right? 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. All right, so let's go. -2 goes to 1 over 36. So that is so small. This is 4, right? We want it to be way, like almost touching the line here, not quite. Same thing, -1 is at 1/6. It's not even at 1 yet, and this is 4. So it's going to be so far below. About there. 0 goes to 1, and again, my scale, this should only be a quarter of the way up. It's kind of hard to do that. But 1 goes to 6. So if this is 4, this is 8. So it's going to be halfway between there, like this. And then 2 goes all the way up to 36. So 2 just shoots way up there. We can see how quickly exponentials grow. All right, now this exponential function has something what we call a horizontal asymptote. Asymptote. A-S-Y-M-P-T-O-T-E. All right, my horizontal asymptote. Horizontal asymptote means, draw this in here. Kind of hard to see over that black line. Maybe get a better pen here. Purple. It's kind of hard to see there, but basically it's a line that we're going to get, as we come over to the negatives, we're going to get so super close, but we're never actually going to touch the line y equals 0. That's our horizontal asymptote. And for today, they're all going to be y equals 0. It's never actually going to touch the x-axis or y equals 0. Okay, and then let's just connect our curve. It's going to, again, get really close and then never touch the asymptote. And it's going to shoot way up there super fast. And don't forget the arrows to show it goes up forever. All right, let's try another one. So same thing, except now we have a different a. Right? A equals 1/2. So remember, this is your initial value. So at x equals 0, it's going to be this, and we'll see how that plays out. Even though we have a 1/2 here, this b is still a 6, right? B is still a 6, so this is still your exponential growth. This is your growth factor. So it's going to grow by this, but it's not going to grow quite as fast because we got this 1/2 here. So whatever our output is, it's just the same as last time, except we're halving it. So again, I'll just go and make a t-chart here. X, y, let's do -2. It's kind of a funky line there. 1, -1, 0, 1, and 2. All right, let's plug in here. So we have 1/2, 6 to the -2. Well, we already calculated what 6 to the -2 is. That's 1/36. So I multiply straight across. That's even smaller. So that's 1 over 2 times 36. That's 1 over 72. Super tiny. All right. Here we have 1/2 times, let's see, 6 to the -1. We already calculated that. That's 1/6. So we multiply across. We get 1/12. 1/12. All right. 0. We have 1/2 times 6 to the 0. Again, we calculated that above. Anything to 0th power is just 1. So here we go. Our initial value is not 1 anymore. It's 1/2 times 1, which is 1/2. And there we see that coming true. That's our initial value, or x equals 0. All right, 1. So 1/2 of 6 to the first. So 1/2 of 6. That's just 3. And finally, 1/2 of 6 squared, which is 36. So we get 18. Okay, so let's go ahead and label these guys. We have -1, 0. Oops, -1. Don't have anything handy, so that's -2, 0, 1, and 2. And you can scale this differently because obviously these numbers are smaller, but just to show you kind of the effect of it, I'll keep the same scale. So we'll do 4, 8, 12, 16, 20, 24, 28, 32, 36, just to see it. I mean, you could obviously shrink these because the numbers don't go up quite as high. So let's check these out. So -2 goes to some crazy tiny number, 1 over 72. And just for reference there, 1 over 72, if we punch that in our calculator just to see what type of decimal that is, right? 0.013888888 forever. So super tiny, it should be super close, but not quite touching the x-axis. Same thing with -1, super small. 0 goes to 1/2. Remember, this is 4, so you should be only 1/8 of the way up here. 1/8 of the way up. 1 goes to 3, so 1 is still, it's like 3/4 of the way up to here. And then 2 goes all the way up to 18. So we got 12, 16, and 20 here. So 16 and 20 should be halfway between these guys right there. So we still have a lot of growth here, but again, it's not quite, it's only going up half the speed of the other one, the first one, because of that 1/2 in front. So draw our curve. And let's not forget our asymptote.